Okay, we've seen in the previous chapter that we can use the transistor either as a switch or for amplification. In this chapter, we're going to look at transistor biasing circuits, where we're going to use the transistor as an amplifier. Section 5.1, firstly, the DC operating point. If you can recall that we have discussed that the amplifier should be biased first before I can use it for linear amplification. But let's have a look at the textbook. I've marked some sections there that I want you to mark. On page 217, the DC operating point. You can mark in your books the same as I have here. It doesn't mean that the rest of the chapter is not important, but these are just the more important facts. Right, the transistor must be properly biased with a DC voltage in order to operate as a linear amplifier. A DC operating point must be set so that the signal variations at the input terminal are amplified and accurately reproduced at the output terminal. I want that microphone or that CD player that I'm playing, I want that small signal amplified so it sounds exactly the same and clear. Only it must be amplified. So that is linear amplification. There shouldn't be any distortion. As you've learned in chapter 4, when you bias a transistor, you establish the DC voltage and current values. This means, for example, that at the DC operating point, IC and VCE have specified values. The DC operating point is often referred to as the Q point, the quiescent point. This is very important. Before I'm going to use a transistor circuit for amplification, I have to bias first. Otherwise, I'm not going to get linear amplification. Alright, DC bias. Bias establishes the DC operating point, Q point, for proper linear operation of an amplifier. If an amplifier is not biased with the correct DC voltages on the input and output, it can go into saturation or cut off when an input signal is applied. Figure 5.1 shows the effects of proper and improper DC biasing of an inverting amplifier. We will discuss the inverting amplifier in more detail as we get along, but in the introduction in the previous chapter we've seen that for that specific amplifier the input and output signals were 180 degrees out of phase. That's why it's called an inverting amplifier. Anyway, if we go and have a look at figure 5.1, here's some examples of what we are talking about at this stage. Firstly, linear operation. That is what we want. So there's my input signal. This is just the amplifier symbol, which you will get familiar with in later stage as well. And I can see my output signal is an amplified replica of the input signal, though it is 180 degrees out of phase. Okay. The B part there, non-linear operation. There is my small input signal. And on my output signal, I can see there is distortion. We'll discuss the reason for it now, but you can see, in this case, my Q point was too close to cut off, so I can see here. The reason why it's on top is because the signals are inverted. I know that my cutoff point is at the bottom of my load line. Anyway, the last one, the nonlinear operation. Input signal, output signal in this case, you can see it's clipped at the bottom, means that it goes into saturation, which is on the top of my load line, but it shows at the bottom of the output waveform because it is 180 degrees out of phase. Anyway, let's do some revision about establishing the load line, getting the collector characteristic curves, and so forth. We have seen, if I have a simple circuit that I have here, a DC bias circuit, there's my biasing voltage called VBB. Variable in this case. Why is it variable? Because I want to adjust VBB, which will establish IB for me. IB, I can see here, as I increase VBB, I get all these different IBs. Okay. What do I know about IB? I know this formula. IC is equal to beta DC times IB. So I can see as I increase IB, I assume my beta DC to be fairly constant, although we know it isn't. I can see that IC will also increase, and I can see it on the characteristic curve of my transistor. Remember, my transistor's characteristic curve is on the axis of IC against VCE. Alright, so as I increase the current, I can see also that I have an increase here in my IC values as well. Alright, for a specific circuit like this as well, I know that I can keep on increasing IB up to a point which is called the maximum current. We actually call it the saturation current. The ideal saturation current would be, well, saturation current would be just below the knee, my maximum current. But if I say it's the ideal current, ideal means if I know what is the parameters, or remember what the parameters should be for a transistor in saturation. If a transistor is in saturation, it acts as what? It acts as a closed switch, né? So if I have the transistor that's acting as a closed switch, that gives me my saturation point. Ideally, it would have been where IC is equal to IC sat, saturation current, and my VCE be equal to 0, but we know it's not exactly 0 because this is not an ideal device. We assume that VCE saturation is approximately 0.2 volts in this book. Well, I will point it out to you again. Alright, what is the other parameter that's important? The cutoff. Whatever it may be, we know if the transistor is in cutoff. You just open the switch here. I didn't. When the transistor is in cutoff, I know that it acts like an open switch. What are the parameters for the transistor when it acts like an open switch? I know then if IB, in this case of course IB is going to be 0. No? Remember, there's all my different IBs. IB is going to be equal to 0, and if IB is equal to 0, what's going to be happening to IC? IC is also going to be equal to 0. So that's my parameter for the transistor in cutoff. For IC, what should the value of VCE be equal to? Value of VCE is going to be equal to, what am I actually measuring? If I measure here over emitter and collector, what am I actually measuring? I'm actually measuring VCC. So it should be equal to VCC, whatever the value may be. Then we've also learned, if I connect these 2 points, cutoff point and the saturation point, that is called my load line. My DC load line. So along this line that my Q point is going to move. You can see here, as I change these values of IB, you can see where it cuts my load line. That would be the Q point for that IB. That would be the Q point for that IB. And so forth. You can see how the Q point moves along the load line as I change the value of IB. Now we've just seen in the example that I should not bias my amplifier, the Q point, so that it is either too close to saturation or too close to cutoff. Let's look at the first example that we've seen. When I bias it so it is fairly close to cutoff, remember this is my cutoff point. So let's make that my Q point. So what is going to happen? If that is my Q point, that is what's going to give me my DC point, my operating point, my cohesion point, from where I'm going to start to amplify. So once I've done that, then I am going to add, let me just erase this. Once I've biased, then I can add my signal. There's my signal source that I want to amplify. Now what's going to happen? I've already established with a certain IB, which was caused by VBB, to give me this current. So what's going to happen? This signal, this input signal of mine, is going to start riding on that current already. That's already been established. But what's going to happen here if it's too close to cutoff? Remember, it has to operate in between cutoff and saturation point. If it's too close to cutoff, what's going to happen, especially if the signal is a bit large? You can see that it goes into cutoff because it's too close to cutoff for the size of signal that I want to amplify. That's why you can see that portion of the signal is cut off, and when I go and look at the output signal on the previous page, what did we see? If we go back quickly again, what did we see when it's too close to cutoff? On the output, because it's inverted, the top part of the waveform has been cut off. Alright, the other one, if I say for instance I use in this example that 500 microamperes and I cause my Q point to be over there, let's call that Q point 2. So that's when I'm going to start applying my input signal. So my input signal is going to ride there, but see what happens. It's too close to saturation and part of my signal gets cut off. So it's not linear operation, and if I go back to the previous pictures again, we saw that. Clipped by saturation, but it's at the bottom of the waveform because it is an inverted signal, 180 degrees out of phase. So what do I actually want? I want to bias my circuit, so I have to do the design in such a manner that my VBB, which is going to cause my IB, which is actually going to be called my IBQ because it establishes the Q point, I want to be in the center of the load line. I want my Q point there. So I will start applying my input signal there, because now you can see I can use maximum swing. So I can even put in I can even apply a larger input signal and it still doesn't go into saturation or into cutoff. You have to be careful though. Let me just clean this up a bit. You have to be careful though that you don't apply too big an input signal. What's going to happen when I apply too big an input signal? Let's have a look at that quickly. Say for instance now, remember that we had our load line there. There's my load line. I know I have to stay between the cutoff and saturation points. Let's say I use 300. It gives me a Q point more or less in the middle of the load line. There's my Q point. So I'm going to start there applying my signal. What I have to be careful for is I should not apply an input signal that's too large. What's going to happen? If it's too large, it's going to go into saturation and it's also going to go into cutoff. Then it will be cut off on both sides. So even if I do bias my circuit in such a way that the Q point is in the middle of the load line, I still have to be careful not to apply too large an input signal. Then I will have distortion and clipping on both sides. Anyway, that is discussed in your textbooks as well, starting there on page 218 and 219, where they show all these. You can see here basically what they've done. They didn't draw the load line though. It's for separate adjustments. Illustration of the Q point adjustment. You can see how the Q point moves along the line. Actually, yeah. There's my saturation point and cutoff point, DC load line, and I can also then see as I change the currents how the Q point moves along the load line. But remember, I have to remain between cutoff and saturation point. I have to keep that in mind. I want a linear amplifier. I don't want signals to get lost. Here you can see the signals being applied on the base, and if the Q point is in the middle of the load line as indicated here, I will not have distortion. Okay, here it is displayed. The cases that I've explained to you already now. Here you can see the Q point is too close to saturation, and part of my signal is cut off there. Here it is too close to cut off there, and in this case it's been too large. The input signal is too large, even though the Q point's in the middle of the load line. I can see that I have clipping or distortion on both the positive and the negative alternations of my input signal. There is an example on page 221, example 5.1, where they ask, determine the Q point for the circuit in figure 5.7 and draw the DC load line. Find the maximum peak value of base current for linear operation. Assume a beta DC of 200. Okay, I have learned about all the formulas that we are using. You can refer to the bottom of page 221. The bottom of page 221, I can see Q point is defined. What is it defined by? Values of IC and VCE. Remember, it's on the axis of IC and VCE. In other words, I know these formulas. IB is equal to VBB minus VBE over RB, a combination of Kirchhoff's and Ohm's laws. If I look at the circuit, I can see that the VBB supply is 10 volts. I know VBE is approximately 0.7. That's an assumption that we make. Divided by RB, 47 kilo ohms. So I get an answer of 109 microamperes. Just keep in mind, you have to do your calculations accurately to 3 decimals so that we all get the same answers. Don't round off. You have to work accurately 3 decimals and express your answers in engineering notation. Then I can calculate IC because I know the ratio beta. So IC and IB. So IC is equal to beta DC IB. I get an answer of 39.6 milliamperes. VCE, remember, if I measure VCE, what is VCE again? Just to refresh your memories again. There's my collector. There's my emitter. Remember, if I asked you to measure a voltage, say VCE, we read from left to right. So I put the red lead on the collector. I'll put the black lead on the emitter, and I will read the voltage. Is there going to be a difference in this specific circuit? It's not always true between VCE and VC. If I measure with a single subscript, like VC, I measure with reference to ground. Always with reference to ground. Start reading from the left. I will put my red lead of my multimeter on the collector and my black lead on ground, but you will see that VCE and VC is going to be the same because there's no resistor or anything between the emitter or ground. So in this case, these two values will be the same. Not always true, as we will see a bit later. In some of the circuits that we're going to discuss, there's going to be a resistor. So then you have to keep that in mind. There's a voltage drop over that resistor as well. Anyway, I apply Kirchhoff's law as I've seen in the previous chapter. VCE is going to be equal to the supply minus the voltage drop. Where's the voltage drop? Over RC, so it's ICRC, and I get a value of 6.93 in this case. Alright, so the Q point then is, we have established that now because we have calculated IC and we have calculated VCE. So since IC cutoff is equal to 0, you need to know IC sat to determine how much variation in collector current can occur and still maintain linear operation of the transistor. That is important. I know if I go and look at my characteristic curve of my transistor of IC against VCE, that I have to remain between cutoff and saturation points. So keep that in mind. So I have to determine IC sat. What is IC sat? That's the maximum current that a circuit can produce. Now if I go and look at this specific circuit, what limits? What is my limitations? Ohm's law, ne? Ohm's law is I'm gonna calculate maximum current using Ohm's law. So what is Ohm's law? Maximum current I is equal to V over R. Alright, but now I'm looking to maximum current. Maximum current in this case we'll call I sat, so saturation current. What is the maximum voltage? Remember, we're looking at this series part of the circuit, ne? What is the maximum voltage? It's my supply voltage. My supply voltage is actually VCC. I know, those are two C's actually. VCC. And what is the resistance around this circuit? What is the resistance? RC. There is no other resistance in that circuit, ne? So maximum current is going to be determined by my supply voltage and the resistances around this series circuit. Simplified a bit, is not exactly true, but let's stick with it at this stage. Maximum current is then VCC divided by RC. And we get a value of 60.6 milliamperes. Then the DC load line is graphically illustrated in figure 5.8, showing that before saturation is reached, IC can increase an amount ideally equal to IC sat minus IC cube. Remember, we calculated IC cube. So IC sat we've just determined 60.6 milliamps minus 39.6 milliamps. I have a value of 21.0 milliamps. However, IC can decrease by 39.6 milliampere before it's cut off. So it's not exactly in the middle of the load line. Eh? Therefore, the limiting excursion is 21 milliamps because the Q point is closer to saturation than to cutoff. The 21 milliamp is the maximum peak variation of the collector current. Actually, it would be slightly less in practice because VCE sat is not quite zero. That was what I was referring to when I calculated IC sat, because we didn't take into account the volt drop between the collector and the emitter at this stage. But we will discuss it at a later point. Anyway, then determine the maximum peak variation of the base current as follows. IB peak is then IC peak divided by beta DC, which was given as 200. So I have an answer of 105 microamps. Okay, that's the DCQ point. Right, so it's the end of this section. Please, again, same rules apply. You have to read through the section discussed, work through the examples in this section, do the relevant true-false quiz, circuit action quiz, and self-test questions. At the end of this chapter, and then very important to do the relevant basic problems to this section. Up to this stage, it's problems, basic problems numbers 1 to 10. In your homework books, ladies and gentlemen, please remember it's important that you do it in a homework book so that you can ask questions the next time we get together and there's something that you don't understand, and also that you can use it to do revision for tests and exam purposes, and even for future reference if you don't understand anything.